Hello, and welcome to Logistic Regression in Python by me, Dr. Alan Brain. If you have not had any exposure to regressional techniques previously, then please view the courses Introduction to Statistics Parts 1 and 2 and Regression Analysis in Python. All of the files are available on www.drbainstats.com, and please download the zip file Applied Predictive Modeling for Direct Marketing in Python. This course covers sampling data frames to create your build and validation data frame, weight of evidence and information value, building continuous variables, building the model, and most importantly, testing the model, all in an applied manner. So what is logistic regression? Logistic regression is used to calculate the probability of an event occurring. For example, a person responding to a direct mail campaign or a customer going defaulting on a loan. In our course, we will be exploring the likelihood of a person responding to a marketing campaign. Before we proceed, I would like to introduce you to the model development framework. As you can see, there are many steps to build a model and are always surrounded by meetings, especially in a workplace. This course will cover the steps 3, 5, 7, 8, and 9. So that we can build a model, we first need to complete the steps 3 to 7. So number 1, we're going to import the data into Python. Second step, we're going to create 2 new variables, num to help with the analysis, and target. It's based on user response variable. And 3, we're going to split our data frame into the build and test based on a 70-30 split. And for our final prerequisite, we're going to investigate weight of evidence and information value. The weight of evidence compares the non-target over target ratio for that bin against the total non-target over target ratio for the whole of the database. The figure is then converted by using natural logs. Information value calculates how well the variable overall discriminates the target variable. And as we can see, the equation for IV contains the equation for the weight of evidence. First, we're going to calculate the weight of evidence using a fictional variable that has been binned into 5 groups. Column A represents the bin. Column B is the number of non-targets. Column C is the number of targets in that bin. Column D is simply B divided by C. Now E uses a total from column B divided by the total of column C. Column F then compares the ratio of each bin between column D and column E. Column G now applies the natural base log to column F. So this gives us our weight of evidence value. As mentioned previously, information value contains weight of evidence. So now we can see, applying the formula, as long as we add up all the values for the IV for each bin, we can get our information value. Any variable that has an IV less than 0.1 should not be considered for the model build. This reduces the complexity of the model and overfitting. Also, any variable with an IV over 0.7 should be investigated, as they could be very similar to the target variable, therefore artificially increasing the strength of the model. And now we can look at our bin variables. We bin variables to make our model more robust and to limit any overfitting. Rather than talk through the code, I will just briefly explain it. Now step 1, we're going to use the where command. This allows us to bin the variables as required. So by using ages as an example, where age is 18 or less, we're going to label it 18. As 18 and less has already been labelled, the next command covers the age group 19 to 24. Therefore, for age range between 19 and 24, label 24. And so on, until step 5. We tell Python that for any other values, give it a value of 30. This is our catch-all bin, but with age range 29 and under already covered, this value is appropriate. As with all model development, we have to treat the validation data frame exactly the same as we do for the build data frame. so therefore we have to bin the valid data frame as we had the build data frame. So we have removed about 70% of the project time to get us this far, as we moved out to steps 4 to 7, which involves plenty of data cleansing. With our variables binned, we can look at dummy variables. Dummy variables are independent variables which take the value of 0 or 1. As an example, if you use one of our variables, children. Children has two values, yes and no. Creating dummy values of this variable requires creating two new columns. Where children equals y, make this column equal 1, else make it 0. And where children equals n, make this column equals 1, else make it 0. So in essence, for every bin created, we create that number of columns based on each value. Creating dummy variables allows easy interpretation of a logistic model and increases the stability by removing outliers and overfitting. Whenever we create dummy variables, we have to be aware of a dummy variable trap. The dummy variable trap introduces multicollinearity. So if we're using our children variable, for example, for every time children y equals 1, children n equals 0, and vice versa. Therefore, we could use children y to predict children n. To solve this issue, when we create our model, we exclude one of the dummy variables from each of the variables we wish to model. So for example, for children, we would only include children y. The dummy variable dropped is always given a score of 0. Creating dummy variables can be a very long process. Luckily in Python, we can use some code that will do this all for us, as shown here. So number 1, this stage tells Python the variables we want to consider to model, which we've made categorical. Number 2, this creates the dummy variables. And step 3 removes the variables from which the dummy variables were created. This is useful for keeping the data size small. And now we've got the variables we want to include in the model. Stage 1, this tells Python the variables we want to consider to model, which we've made categorical. And number 2, this created data frames to build our model. Data frame X contains all of our variables we wish to use. And data frame Y, that is our target variable. Additionally, please note that each variable misses one bin due to the dummy variable trap. Sometimes during model building, we may have hundreds of variables that we wish to consider. This would lead to the model being overcomplicated and will suffer from overfitting. This stage allows us to reduce the variables that we want to include in the model. Now we're going to use regressive feature elimination, and this is a code that does it. And with this tenet, we want the top 14 variables. We can see though, the results is not that straightforward to interpret, which brings us to the next slide. The support and ranking are based on column order, so it can be easily deciphered, as shown here, which have been put into a table. From the table, credit card N is the weakest performing variable, which is rank equals 4. Additionally, those variables not strong enough for a model will need to be dropped, which is main salary group 24,000, main salary group 0. From the above, it shows that for the variable main salary, we should only consider over 0 to 12,000 as one bin, and the others should be set as 0. Due to this scenario, we're going to drop the variable main salary. And finally, our model code. Step 1. These are the final variables we want to include in our model. Step 2. As Python does not produce an intercept automatically, we have to create a new column with a number 1. And step 3. Our model, which we can show on the next page. And these are our initial results. At this stage, our main concern would be check the Z values. All of these values need to be less than 0.05, otherwise they will need to be rejected. This is because any value greater than 0.05 would mean that over 5% of the time, the value was predicted by chance, so it's not reliable. The other main negative or valuable information are the coefficients. Technically, these are variables for our model, but without any testing, we are not sure if they should be used. As shown, creating a model is very simple and straightforward, but now we need to know if it's any good. So this brings us to a measurement, and we're going to use area underneath the curve and Gini. The area underneath the curve produces a score between 0 and 1, and a score of 0.5 means that there's no power. With any values closer to 1 means it's stronger. And then the most common used measurement technique is called the Gini, or sometimes the sum as D. The Gini measurement tells us how well the model separates the targets and non-targets. And this is an example of the graphs. As you see, for AUC, it is all of the chart. With a Gini chart, it's just the area above the line. So how do we calculate AUC and Gini? Python does not provide the model performance in its results, so we must write more programming code to calculate AUC and Gini. To calculate AUC and Gini statistics, we need the probabilities applied to the model data frame. So, using the where statements, we're going to apply the scores, same as a binning code. And the coefficients come from our results previously. The next stage entails adding up all the scores and converting this into a probability. With our coefficients applied to the build data frame. Our first stage is now straightforward. We add up all of the different scores, including the intercept. Then step 2 involves using our equation and converting the top score into a probability. This probability tells us the likelihood of a customer responding to the marketing campaign. And now we can calculate our Gini statistic using the area under the curve statistic. This produces a score between 0 and 1. A score of 0.5 means that there's no power, with values closer to 1 being more predictive, which will lead us to calculate the Gini, or sometimes known as the sum as D, as shown in the equation on the slide. So step 1 entails importing our libraries. Step 2, calculate our AUC. 3, apply our equation to get to Gini. And number 4, we're just going to print our results, as we can see on the slide. You may have a different AUC or Gini, as it depends on the sampling. With the model created, we can now test it to see if it's suitable to be used elsewhere. Overfitting tends to occur when there are too many variables or bins compared to the number of targets. This tends to produce a model that is counterproductive to common sense and not perform to the same standard on a different data frame. A simple test to measure overfitting in a model requires using the validation data frame. The validation data frame must be binned exactly the same as the build data frame. Then a comparison of their Gini scores is conducted to check if they are similar, within 1% of each other. Scoring up the validation data frame involves using the exact same model that was created on the build data frame. That model was then applied to calculate our Gini. With a slight decrease in Gini between the build and validation data frame, but within 1%, this tells us that the model is stable. If it had changed way over 1%, then we could use bootstrapping, which is introduced on the next slide. The bootstrap method works by taking a random sample of the validation data frame 100 times to check the ranges of different Gini scores calculated, as shown on the code. Step 1, we will install the library we sample, which allows us to get random samples. Step 2 provides the key information regarding bootstrap parameters. Step 3 completes our bootstrap function, and 4 produces our quantile upper and lower 25% figures. If the bootstrap method fails, then the following should be considered. Remodel the data frame but exclude some of the variables until the Gini stabilizes. Return to the beginning and resegment our build and validation data frames. Our next test involves correlation. Correlation between variables can cause issues. Correlation occurs when two or more variables behave very similar. When this happens, the variables are more likely to predict each other rather than the target variable. We did not conduct the correlation analysis previously, as we did not know which variables would be in the model. Removing variables earlier may have removed strong predictive variables and leaving the less powerful but still predictive variables behind. Correlation analysis is conducted as follows. We can use a scored data frame and use the scored variables for the correlation test. As we have done all the hard work previously by scoring up the build data frame, the next steps are quite easy. First of all, we're just going to create a data frame with just required columns. This makes the correlation test easier. Our second step is a simple line of code, create a new data frame with our correlation results. Called data frame was copied and pasted into Excel, and using conditional formatting, it's easily observed if any variable suffers from correlation. Obviously, variables are correlated with themselves, but not with any other variable, so the model passes this test. If correlation had occurred, we would have to drop one of the correlated variables from a model. This would not make a big difference to the model performance and would mean a more stable and usable model. Our final test is reverse causality. Reverse causality is another important test we must consider when developing models. We need to test that the parameter estimates, coefficients, behave as they should. As an example, they mimic the target rate patterns. When a model estimates perform opposite to the target rates, this is classified as a reversal. As we've already scored up our data frame, next stage is straightforward. The easiest way to observe reverse causality in our model is by creating a chart. First, step 1, we must produce our data frame for us to produce our chart of score versus target rate. Step 2, the columns have been renamed, so the plot code requires little amendment, just a title. And step 3, the code to produce our chart contains 2 lines. As you can see from the chart, the estimates and the target rate behave the same. The code for the other variables is just the same, just requires change of the data frame name and title. So rather than print out all the graphs which have no reversals, we'll review an artificial chart with a reversal. Below is a chart created in Excel to demonstrate the reversal. From a chart we observe that the 2024 population does not perform as expected, thus potentially giving those customers a good score. There are 2 ways to solve this: rebin the variable, potentially making the second bin 22 to 30, or drop the variable. Usually this scenario occurs by the variable reacting with different variables within a model. But, as mentioned before, our model passes this test. And that's it. Producing a model in Python is quite simple, but ensuring it is suitable and can be used in a live environment requires a lot of testing. This presentation removes 90% of work that is normally necessary to construct a robust and powerful model. Thank you. Additional material is available in the reasonably priced Python book, which is available on Amazon